Okay, in this video I'm going to do a little bit of an overview of the National Energy Code of Canada for Buildings 2020. I'll specifically, for the most part, cover Part 3, so Division V Part 3, and generally speaking, we'll take a look at the prescriptive path in a little more detail. I'll talk about the trade-off path, and then I'll just talk about what the performance path is. I won't get into the details of the performance path. But generally, there's three approaches to meeting the energy code. And those are your three options, so we'll take a look at those. And just jumping right in though, the first thing I want to take a look at is the application of this code. So we'll go to Division A Part 1, Section 1.1 in the general. And I've highlighted a sentence here. And basically this article here is describing, okay, when do you have to use this code? And what it's saying is for all new buildings and additions to buildings, you have to use this energy code. And if you do any alterations to buildings that use this code, and you don't need to use it for farm buildings. So it's not all buildings, it's all new buildings described in sentence 13321 of Division A of the National Building Code. So let's just jump over to there and see what that says. Okay, so here's the National Building Code here, and this is the article that talks about whether you need to use Part 3 or not. Okay, so there's another video on this, but generally speaking, when you're using the National Building Code, there's a Part 9 and a Part 3 that are generally used by architects. And the Part 9 typically, just as a refresher, if you haven't seen that video, the Part 9 typically tends to be used for lower density housing. There is other things that it could be used for, but generally I'd say for the bulk of it, it's used for lower density housing, maybe some medium density housing as well. But all other buildings generally fall into Part 3. And so basically what the energy code is saying, that entire document is saying you only need to use that if you're using a Part 3 building, and when you're using Part 3 for a building, you're also triggering Part 4, 5, and 6 as well. They just go with that. So I guess in a nutshell, if you know you have a Part 3 building, because it's out of the parameters of Part 9, which in a nutshell is 600 meters squared, more than 3 stories in building height, and you can't have, say, for an example, an A2 occupancy use in the building. There's other things as well, but generally speaking, that's kind of what it is. So if you know you're going to use Part 3 of the building code, then automatically the National Energy Code for buildings applies as well. And so the question might come up of, well, if the National Energy Code only applies to Part 3 buildings, what do you do in Part 9? So if you're familiar with Part 9, so it's in volume 2 of the National Building Code, Part 9, basically the energy code requirements are in Section 936, energy efficiency. So if you're using a Part 9 building, you would go through 936 to find, I guess, the comparable requirements as far as energy code goes in a Part 9 building. So I won't focus on 936 in this video, but just be aware that this only applies if you're in a Part 3 building. So other than that, the only other thing that I would say you'd use maybe on a daily basis would be maybe the terms and abbreviations before we get into Part 3. So I won't go there. I'll just zoom down to Part 3 here, and we'll take a look at the general statement here. And now this is where in 3113, this is where it tells you that compliance with this part, so the Part 3, shall be achieved by following a prescriptive path, a trade-off path, or a performance path. Okay, so we'll look at those in a minute. Next, we'll go forward to 3116. And so 3116 is just saying that when you do the calculations for fenestration and doors, you have to include the frame and sash members. And then finally in section 3.1, we'll go to 3117. And this one's actually one of the more interesting articles because it's got a little bit of history to it here of how it's changed over the years. So in calculating the overall thermal transmittance of assemblies for the purposes of comparison with the provisions in section 3.2, the effect of thermal bridging shall be considered for closely spaced repetitive structural members such as studs and joists, and so on and so forth, lintels and sills and plates and all these things. So basically it's saying, every stud in the wall has to be considered in the calculations. As an example, thermal bridging for any major structural elements that penetrate or intersect the building envelope need to be considered as well. And importantly here, the junctions between building envelope materials and components and assemblies. So, glazing assemblies, spandrel panels, how parapets meet walls, and roof-to-wall junctions and corners, might have more studs in it and this type of thing. And all that has to be taken into account is basically what it's saying. So edges of walls and floors. So basically everything is being included in the calculation. Some things that are excluded are pipes, ducts, and equipment, and through-wall venting you can not include in the calculations. And also it excludes fasteners, so any screws or something like that penetrating the envelope. And so why I think this article is really interesting is because I'm going to go back in time here and show you how this article has changed over time. So this is the 2020 version. The previous version to this one was the National Energy Code for Buildings 2017. And this article is, let's just see, I think it's exactly the same as the 2017 one. It hasn't changed. But the Energy Code prior to 2017 wasn't at all like this. So when the 2017 Energy Code was being introduced, it caused a huge stir in the architecture and construction industry, because basically the old, I guess it would have been the 2011 Energy Code, didn't require a lot of this stuff that's listed in here to be part of the calculation. So I'm going to open that up and let's take a look at that. And so here we're looking at the 2011 one, the same article. And some other things that need not be taken into account was structural members such as columns and spandrel beams that are parallel to the plane of the building envelope and partly penetrate that building envelope need not be taken into account. Okay, so in 2011 you didn't have to worry about that. Major structural penetrations such as balcony slabs, beams, girders, columns, ornamental, blah, 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 all that stuff didn't have to be taken into account for the purposes of calculating overall thermal transmittance. And that was provided that the sum of the cross-sectional areas of those major structural penetrations is limited to a maximum of 2% of the above ground building envelope area. So as an example, I think a good one is maybe the balcony slabs. Let's take a look at that situation. So for example, a balcony situation, say in a concrete building, so the exterior wall is going to be here, or the window wall will be between these slabs here on this one. And this is going to be a balcony over here. So you'll see that there's no thermal break between, the building envelope portion and then where the balcony slab comes out. So I know if anybody's watching this from maybe Europe or something, you'd be shocked by this, but this is how we build it here. It's even now, even with the new energy code, it's not forcing balcony break products right there, even though in this situation there's products that would work there for sure. And so anyways, in 2011, or I guess up until 2017, this was the energy code in use, and it was easy to meet the energy code, let's put it that way. It's just the way we built buildings generally met the energy code, and a lot of these items were excluded from the calculation. So forward to the 2017 National Energy Code, and it was this sentence, so that same sentence 3117, that changed quite a bit, and then all of a sudden said major structural elements that penetrate the building envelope do have to be included. And although the 2011 Energy Code talked about studs having to be included, it didn't have this sentence C either that talked about the junctions between components in assembly. So like a window to a wall, for example, how that window sits in the wall, and that actual connection between the two, where you're basically going to have no insulation. Now you do have to include that as an example. So the whole list of stuff here was added. So when 2017 came out, it really did. It kind of had the industry really wondering what this meant. And so that's when a big change came, and anybody that was around in the industry around that time would remember that. And it was really this sentence, this 3117, that really changed the whole game. And what kind of ended up happening was, we're going to look at the prescriptive approach to the energy code here, but most buildings aren't even done in the prescriptive approach. So you would certainly use a lot of the parameters out of the prescriptive approach, but generally what's being done is the performance path. And it's really when the code started to add all this stuff having to be calculated, it really created a new consultant out there. So energy code consultants basically created a whole new um, bunch of people doing a lot of calculations, basically. Another consultant, basically, is what it ended up happening. Okay, so before we move into the prescriptive path, I just want to back up a little bit and go to Division B, Part 1, the general section here, so 112 under compliance. This is where it talks about the options of doing the prescriptive trade-off and performance compliance. And there's a reference to the appendix here, so we'll just go there and flip forward a couple of sheets here. And here's where they give kind of the summary of what these mean. And so, in a nutshell, prescriptive path means you're going to meet all the requirements listed in 3.2. You're just going to meet or exceed them. That's the prescriptive parameters, and then if you meet or exceed them, then you're meeting energy code basically. The trade-off is just saying that if you, and there's limitations to the trade-off that we'll look at, but it's kind of saying that if you exceed say some performance in one area, you can trade that off to another area of the building where you didn't meet the requirements, as an example. So it's a little bit of a trade-off to the prescriptive path there. And then the performance path is basically when you do energy analysis of the building through, so energy modeling basically. And how that's kind of approached is, we won't get into the detail of this in this video, but they do two energy analyses. So one's the building as if it was met using the prescriptive requirements, and that kind of gives the target performance. And then the other model or analysis is the actual design for which the building permit is requested. So meaning, I guess what it is kind of, there's a much broader trade-off, I suppose, that could happen, or just more flexibility to weave around some of the hard prescriptive elements maybe in that we might find in the prescriptive path. And so, for example, you could trade off, maybe you do a higher efficiency mechanical system instead of doing a certain amount of insulation on the wall and stuff like that. So it kind of increases, I suppose, the trade-off in a way. But anyways, it's performance path just means you're doing an energy modeling approach basically, which is generally what most, I would say most Part 3 buildings are going that route, and having an energy consultant involved at some level. Okay, so in the prescriptive path, maybe the first thing I'll just mention here is 3212, continuity of insulation. I mean, that's pretty straightforward. It's just saying, you have to ensure continuity of insulation, even if you have construction joints and stuff like that, you got to achieve that continuity. Next item here of importance, 3214, so allowable fenestration and door area. So this is basically where the energy code's telling you that if you're going to meet the prescriptive approach, you can only have so many fenestration, you can only have a maximum amount of fenestration percentage on your building and door area. So fenestration and door area. So the easy way to figure out what does that mean for me is just go to the appendix. I mean, they show you the calculation to do this, but you go to the appendix and you find your heating degree days in your climatic data for the city you're in. So where I am, we're 5,000 heating degree days. So 33% glazing is the maximum fenestration and door percentage that you could have around the whole facade of the building, basically. What's kind of interesting is that if we went back to the 2011, that 33% actually it was there as well. I don't know. I guess people just weren't maybe. I don't believe that it was being respected much. Let's put it that way. But anyways, it still exists. So there's if you're going for the prescriptive path, then you'd want to make sure you maintain a maximum amount of fenestration and door area, and that's just because they're not as well insulated, right? So that's what that's all about. And if you have skylights on the roof, they can't be more than 2% of the gross roof area. Okay, so next we'll move into 3221, which is vestibules. So this just tells you that you have to have some vestibules in certain areas, so not everywhere, but just read through that. Some vestibules are required. 3222 is the thermal characteristics of above ground opaque building assemblies. So the overall thermal transmittance of above grade opaque building assemblies can't be more than what's in this chart here. So if you have a wall above grade, you just look at what zone you're in. And so for example, I'm in zone 7A, and my heating degree days are 5,000. So my U value is 0.215. So they're showing the U value, so that the lower that number gets, the better as far as heat loss through materials. So there's your walls, there's your roofs, there's your floors. And so if this is the U value, probably most people work in RSI, so that's the reciprocal of that. So you just do 1 over 0.215. So 1 over 0.215. So that's basically saying you need an RSI of 4.65. And so if you work in R instead of RSI, so the imperial units, then I just usually go to a web page and do that conversion. So 4.65 is an R26.4, which is actually kind of curious because this is a fairly new document when I'm recording this, so I'm just going through this myself to see what's changed, and this number is different from the 2017, but not in the direction I would have expected. So I've opened up the 2017 here, and it used to be a 0.21 was required. So if you convert that, in the 2017 energy code, a 4.75-ish RSI was required. Now only a 4.65 RSI is required, which is kind of interesting. You'd think that would go the other way, but there must have been some reason they moved that down a little bit. It's interesting. Okay, then we move into 3223, which is the thermal characteristics for fenestration. So kind of the same idea here. Your fenestration has to meet a certain U value, which in my mind generally means products you buy are going to meet that minimum, or else I suppose some might not, but you would think if people are going to buy it, you'd kind of want it to meet the minimum of the energy code, or you might have a hard time selling it. But certainly, if you look at the number that's shown here, the U value there, you could beat that U value doing a triple glazed, for example, rather than a double glazed. There are systems out there that could beat that. So maybe that's something we could look at when we look at the trade-off area. 3224 just gets into doors and other access hatches. Same kind of idea there. Then 323 gets into your building assemblies in contact with the ground. So generally this would mean like your foundation walls or slabs on grade or something like that. Or if you have a plaza deck situation, this is where you'd be. These would be either a wall, roof, or floor in contact with the ground, and then you just have a different set of numbers there to deal with. But much like the opaque walls above grade, it's kind of the same idea. So you just have to do a little bit of conversion there and figure out, for example, how much insulation is required on the outside of the foundation wall. Which is actually a pretty easy thing to calculate because you don't really have any penetrations through that insulation. So the above grade walls, you have clip and rail systems holding your cladding up, or brick ties and all these types of things that would have to be included in the calculations. But for your foundation wall, generally speaking, whatever the requirement is here, let's just take a look at that. So 0.284. So that would be about an RSI of 3.5, which would give you just under an R20. So looking at some just rough rules of thumb for insulations. So a mineral wool maybe R4.5 per inch-ish. and a XPS insulation would be about R5 per inch. So you'd be looking at about 100 millimeters of insulation on the foundation wall to meet the energy code there. And something else I'll just point out here is that the insulation only needs to go down so far. So that's in sentence 3. Next, 3232 is talking about the thermal characteristics of roofs in contact with the ground when that roof is less than 1.2 meters below the exterior ground level. So for example, a plaza deck, like maybe the parkade, underground parkade extends out farther from the exterior wall above. And so you have a plaza deck situation. So, there's actually 2 sentences here. One talks about using the values in the chart up here, but there's also a mention of a semi-heated building. So, if you know that say that parkade is going to be kept at a lower temperature, it looks like it's below 15 degrees, then you can go down a notch on your heating degree day from the 18 degrees Celsius one to the 15 degrees Celsius one. So that might take you down a zone basically. In 3233, so the thermal characteristics of floors in contact with the ground, so a slab on grade needs to be insulated, but just sentence 3 is kind of important here that, if you don't have any embedded heating ducts or something like that, or cables or something, then the insulation only needs to go in a certain distance from the perimeter. And then just moving on to 324, so about air leakage, so basically you have to have a continuous air barrier in your building, basically, is what 3241 is talking about. And then how well does the overall air barrier assembly have to perform? Well, it's 0.2 liters per second per meter squared at a pressure differential of 75 PA. So, so you do blower door tests to ensure that you meet the air barrier requirements. Okay, and so that's kind of the most important things out of the prescriptive path section. Just moving into the section 3.3, the trade-off path. So the only thing I want to point out here, so there used to be, actually they call it a simple trade-off path, and if you're just kind of getting into the energy code for the first time, you'd be like, well, why is it called simple? Because I don't see anything else, basically. That's all there is here is a simple path. There used to be what was it called? Let me just check. I'm just going back to my 2011 energy code here. So there used to be a simple trade-off path, and there used to be a detailed trade-off path. So they've dropped the detailed trade-off path. Yeah, it was actually dropped in the 2017 version as well. But it looks like they just kept the same terminology there. So what's kind of important out of this is, so this is telling you that the vertical above ground portions of the building envelope are only permitted to be traded off against other vertical above ground portions of the building envelope. Meaning, like I mentioned earlier, if your windows, say your windows that you're putting in are exceeding the requirement of the energy code, but maybe your opaque walls aren't quite meeting the energy code, that they're both on the vertical face, so okay, so the wall and the glazing, so then you could trade the two off. But you cannot trade say a lack of insulation on a wall, you cannot trade it off to more insulation on the roof. Okay, so it's saying it has to be vertical to vertical, and then the next sentence is horizontal to horizontal. So again, you can't just pile a bunch of insulation on the roof and then not do much insulation on the walls is basically what these sentences are saying. But there is some other simple trade-offs you can do there. So as an example, maybe on the horizontal items, like maybe for some reason, I don't know, you have a rooftop deck or something like that, and you have less insulation under that occupied area than is required. So you have to put more insulation elsewhere on the roof to make up for it. So you could do that, for example, in a horizontal situation. Okay, and then the last section here that we're going to look at is section 3.4, so the performance path. And basically what this is just saying is if you don't comply with the last 2 sections we looked at, so 3.2 and 3.3, then you have to comply with part 8, and then so your energy modeler would go to part 8 and work through that section there. And so just some other things I'll point out here is like your part 4 is your lighting. Okay, so your electrical consultant would be looking into that. Your mechanical consultant would be into part 5 and 6, and it looks like your electrical consultant would be in part 7 as well. And so obviously, even if you're going there, the performance path, you would generally want to be very aware of your prescriptive requirements because, again, like you still have to meet or exceed it in some way. So the closer you can get to the prescriptive items, the easier it'll be, I guess, to make sure you meet or exceed in the performance path. And I guess lastly here, don't forget always the notes to part 3. So any references to the appendix, should be looked at. I have a few things highlighted here. One of the important ones, actually, maybe I'll point out here is thermal bridging calculations. So if we went back to the requirement on an opaque wall. So again, just with my example, so I'd require an RSI of 4.65 here, or just under R27 is what that works out to. So again, that's not just the insulation. That's, you have to consider all the penetrations through that insulation. And so, if you're doing like a rain screen, lightweight cladding, like a composite metal panel or something like this, or you're doing brick and there's going to be brick ties, these things have to be accounted for. So then the question becomes, well, how do you do that? And so therein lies one of the challenges of doing the prescriptive path. There's a lot of calculation to do because it's not just that. Again, if we go back, you have to figure out all the corners and buildings, and if you have a flagpole going through there, like everything, basically. The connection of the window jamb to the wall and all this type of stuff has to be considered. And so, just as an example, where I live, so if we just go with the R27. If you assume roughly R4.5 per inch for mineral wool insulation, you're looking at 6 inches, so 150 millimeters of outside insulation on a building. So I guess just the 150 millimeters of the mineral wool insulation would give you roughly R27, but that doesn't include all the penetrations through that insulation. And so the common approach to commercial construction around where I live is something like this. So, behind here there's a steel stud wall, and then the sheathing, and then in this case the air vapor moisture barrier. And then it looks like they've got the 150 millimeters of insulation here, but they need to put a cladding on there, so you can't attach the cladding to the insulation. And so what you're seeing here is a clip and rail system. So there's some clips going through the insulation and then holding a continuous rail. So it used to be a continuous Z-girt would go through the wall, or through the insulation, I should say, for the cladding to attach to. So that's gone away because of the current energy code. So now it's these clip and rail systems that are being used, because then you just decrease. If this was a continuous Z-girt, I might have a picture of that actually. Here's an example of a Z-girt. So this is how it used to be I'm going to say the 2017 energy code. There'd be a continuous metal Z-girt put through the insulation for the cladding to attach to this rail basically here. So that's bad, obviously, because you lose a lot of heat through that metal. And so actually, here's a really good image of this clip and rail system here. So this is a very common one right there. So a whole bunch of different manufacturers for these clip and rail systems. So again, in behind this membrane you see here is the sheathing, and this is the air vapor moisture barrier. And there's the outside insulation, mineral wool, and instead of a continuous Z-girt, so this in a vertical fashion here versus the picture I just showed you before was horizontal. It just depends on the orientation of your cladding. So in this case, I needed a vertical rail. So instead of having a continuous Z-girt going through the insulation, we now have gone to this clip and rail systems that most of them are metal, but they have a low conductance spacer basically between the metal and the sheathing, which is kind of interesting because the sheathing itself kind of acts like a thermal break, I suppose. So I'm not too sure if it's doing a lot, but anyways, it's something. And there are other clips out there that are not metal at all. So there's clips that are all fiberglass, for example, which is obviously lower conductance, so they'll perform a little bit better than these ones, for example. So anyways, there's lots of different clips out there to hold these rails. But again, so now if this was 150 millimeters of insulation, then this part of the wall here would essentially meet that R27 or RSI 4.65, pretty close anyways. But once you consider the thermal transmittance through these clips, and they're going to be every so often, so there'll be one about there or whatever, then you're not going to be meeting that RSI 4.65. So what to do? So in the appendix here, it talks about this. Okay, so thermal bridging calculations. Acceptable sources of information for calculating the effect of thermal bridging are the building envelope thermal bridging guide, which is available through BC Hydro. Okay, and there's some other stuff here as well. So that's interesting. So if we open up this BC Hydro document, they've actually tested a whole bunch of very, very common wall assemblies and curtain wall assemblies and roof assemblies and all kinds of stuff, basically. And so you could use that guide to figure out, well, what is my effective RSI value through that wall. So the effective would be including all those clips and rails, for example. And so this is a free document, you can get off the internet. So the building envelope thermal bridging guide, and they update it very often. They keep testing different assemblies, basically just common assemblies that are used. So, as an example, I think I've added maybe my own bookmarks in here. But if we go to the ISO clip, which is the one we saw in the picture I was showing, this one right here is the ISO clip. And you'll see here that they've shown the wall assembly that they've tested. Okay, and so this would be a pretty typical wall. So gypsum board, steel studs, sheathing. They didn't show the membrane on there because you wouldn't really get much for it, I guess. But there's your ISO clip, and then the rail, and then the mineral wool insulation, and they describe all the assembly components here. And elsewhere in this document, they give you the findings of testing that, basically. And so if I just scroll down to this section here, ISO clip. So here's that wall, and here's the output, basically of testing it. Okay, and so you got to know your stud spacing and a whole bunch of parameters. So how often are the clips? Are they vertical? Are they 60 inches? Are they 24 inches? Like whatever. You have to know all the specifics of what it is you're doing. But then, you can get your RSI value out of that. So let's just say your stud spacing was 24 inches on center and your clips were 36 inches spacing. And so the U value there is 0.258. So not quite meeting the requirement, right? So what was that? So 0.258s are 3.87, or sorry, RSI 3.87, and the requirement was 4.65, I believe, going off the top of my head. And so you have to make that up somewhere in the trade-off. So maybe you have better performing windows. Maybe you've done less than the 33% glazing. All kinds of stuff. But anyway, this is a useful document to start to better understand what is the effective, I guess without modeling stuff yourself, you could use Therm or something to figure it out yourself, but a lot of it's already been done for you in this BC Hydro guide. And so if you were doing the prescriptive approach, you could actually, because of this sentence here, you could actually clip out the BC Hydro guide wall and say, here's what I'm using, and so on and so forth. And so that's kind of interesting. But, anyways, don't forget about the appendixes. That's not much stuff in there, but that's a really interesting article there. And so what do we see right now in around where I live in Calgary? So, but going back to the 2011 code or energy code, back in those days, the normal amount of insulation on the outside of a building would have been maybe 75 millimeters. The exception would have been 100 millimeters. Once the 2017 energy code came into effect, pretty much from what I'm seeing, the standard is 150 millimeters is being put on buildings. So as we just saw, we just saw a picture of 150 millimeters with a clip and rail system that probably isn't going to meet energy code in a prescriptive form. So again, this is why one of the reasons that people are going to the performance path You know, I suppose you could go to 200 millimeters of insulation, but there might be some complications with how many clips can actually manage that amount of insulation. There's all kinds of parameters, but anyways, it doesn't really matter. The point is the norm has become the 150 right now, and anything beyond that would kind of be the exception. And so I guess you know, so that's why I guess a lot of the buildings are being done through the performance path, and I believe a lot of the makeup. So yes, the architects, the design community has increased the insulation because of the energy code. It's still not quite there, so I think the rest of it's being made up in the mechanical systems for the most part. Because I'm still seeing buildings with well over 33% glazing as well. So I think when you get into the energy modeling, probably a lot of that's being made up through mechanical systems, exceeding the requirements of the energy code. So anyways, that's kind of a lowdown of the National Energy Code for Buildings 2020. Hopefully you learned something from that.